Swayam Prabha. Digital India. Educated India.
Today we will talk about unsymmetric bending. You have already studied bending of beams with symmetric cross sections, and also when the loading was in the plane of symmetry. So, let us consider a situation like this, that you have a beam of uniform cross section. The cross section is like this, and this y axis is an axis of symmetry. The beam was bent by applying moment mz like this. Then you have already derived the flexure formula, which gives you the stress distribution in the cross section, which is like this, minus sigma x by y is equal to mz by izz equal to E by r, where sigma x is the stress acting at any point on the cross section in the x direction, y is the distance of the point from the z axis, mz is the moment, izz is the moment of inertia of this cross section about the z axis, E was the modulus of elasticity of the material, r is the radius of curvature. Now, let us try to consider the moment of the stresses which are acting on this cross section about the y axis, which is the axis of symmetry. Now, if we consider the moment, this is let us say that this is an area dA. So, on this area, if x axis is out of the board, then we have stress sigma x acting there. So, therefore, the force is sigma x into dA, and the moment about the y axis will be z into sigma x into dA. So, if we integrate, that gives us the moment, and if you do this integration, we get the value m by izz yz integration over the whole area. And you can recognize that this particular integration is nothing but the product moment of inertia. So, we can write this thing as minus m by izz into iyz. We assumed in the derivation of this flexure formula that y axis is an axis of symmetry, thereby meaning that this product moment of inertia iyz is equal to 0. So, that was the underlying assumption in arriving at the equation number 1. Suppose you have a situation iyz is not equal to 0. Then in that case, sigma x cannot be determined by this formula, and we have to find out a different route to arrive at the stress distribution on a cross section. And this can happen when you have a cross section like this. Think of a cross section wherein we have the y axis and z axis located like this, and this is the centroid of the cross section. And in this case, if you try to load the beam in the xy plane, then you will find that you are not going to have iyz equal to 0, and hence we will have difficulty in calculating the stress distribution in the cross section, and it will be improper to calculate the stress by this formula alone. So, that is the object today, that if IYZ is not equal to 0 for a cross section, and if we have bending of the cross section, how do we find out the stresses? In order to do that, one way to go about is find out the directions, let us say y1 and z1, whereby we will have IYZ equal to 0, and then work with those two directions to find out the stresses. I will again repeat, suppose you have a cross section like this and you have loading in the xy plane, then in that case if you work with this system, you are not going to have IYZ equal to 0, and you cannot find out the stress distribution using this formula. Alternatively, what you can do is that for this cross section you can find out directions. Maybe we would have a direction like this, this is let us say y1, and there will be another orthogonal direction, let us say this is z1. So, this y1 z1 are the two directions which are going to give rise to product moment of inertia equal to 0, and then in that case we can certainly work with this sort of formula to arrive at the stress distribution for a particular loading. So, let us find out the two principal directions, they are called principal directions of the cross sections like y1 and z1. Let us make a start with a general cross section like this, that the beam section is like this is the direction y and this is v. Now, let us consider that we have two directions u and v which are arbitrarily oriented at an angle alpha with the z directions. Then in that case, from geometry we can write that u is related to y and z coordinate of a point by this formula, u equal to z cosine alpha plus y sin alpha. Similarly, v is equal to minus z sin alpha plus y cosine alpha. Now, if I try to consider the moment of inertia about the axis u, then we have to take v square into dA integrated over the whole area. So, therefore, moment of inertia about the axis u is nothing but integration of v square dA over the whole area. So, this is the elemental area which is dA, and this is the distance which is v. So, then in that case it is v square dA to be integrated. And if I now substitute the value of v what we have got here, then we have so it is z square sin square alpha y square cos square alpha minus twice yz sin alpha cosine alpha dA. And this we can write now, we have sin square alpha which is constant, which is not variable of integration. Then we can write this z square dA integrated over the whole area will give us Iy. So, therefore, this is nothing but Iy sin square alpha. Similarly, y square dA integrated will give us Iz. I simply write Iz rather than Izz, so also Iy rather than Iyy. So, this is Iz cosine square alpha, and yz dA integrated, it gives us the product moment of inertia, and therefore, we will have Iyz, and 2 sin alpha cosine alpha we can write as sin 2 alpha. So, that is the expression for Iu, and now we can write sin square alpha as 1 minus cos 2 alpha by 2 and cos square alpha equal to 1 plus cos 2 alpha by 2. By using that, we can rewrite the above expression as Iz plus Iy by 2 plus Iz minus Iy by 2 cosine 2 alpha minus Iyz sin 2 alpha. This type of expression you have come across certainly in connection with the Mohr circle for stresses in 2 dimensions, but note that the expression for sigma x that you had or sigma x dash that you have obtained in terms of sigma x and sigma y, they were little different. So, there are you certainly had noted that there was a positive sign here, but it is different in this case. It is not exactly the replication of the formula that you had in connection with the Mohr circle. By similar procedure, I can now write moment of inertia about the v axis is equal to integration of u square dA over the whole area, and this gives us Iz plus Iy by 2 minus Iz minus Iy by 2 cosine 2 alpha plus Iyz sin 2 alpha. And you can see now that if you add Iu plus Iv, then we are going to get these terms cancelling, and you finally find that Iu plus Iv is equal to Iz plus Iy. So, this is like sum of the two moment of inertia remains constant irrespective of the selection of axis. It is like a stress invariant, the principal moment of inertia sum always remains constant. Now, let us try to see what happens to the product moment of inertia. So, if we now consider the product moment of inertia of the cross section with respect to the axis uv, then we would have I uv, it is nothing but integration of the quantity uv dA to be integrated over the whole area, and this on substitution of value of u and v, so z cos alpha plus y sin alpha minus z sin alpha plus y cosine alpha dA. So, that is the product moment of inertia. And now, if we try to simplify this, it gives us Iuv is equal to minus Iy sin alpha cosine alpha plus Iz sin alpha cosine alpha plus Iyz cos square alpha minus sin square alpha. So, this is the value of Iuv, and this we can now write in terms of sin 2 alpha cosine 2 alpha. So, this will be Iz minus Iy by 2 sin 2 alpha plus Iyz cosine 2 alpha. This is the product moment of inertia. Now, what we are looking for? We are trying to look for two axes u and v such that the product moment of inertia will be 0. So, we can now write the condition for IUV equal to 0. So, that will give us the direction alpha, IUV equal to 0, that gives us directly the direction, let us say that is alpha 1 direction. So, therefore, tan to alpha 1 is equal to minus 2 times IYZ by IZ minus IY. So, that is the angle alpha 1 which U makes with the positive Z axis. So, therefore, this is nothing but angle with positive Z axis. So, now we are in a position to get the direction alpha 1 which will make the product moment of inertia 0. So, these are directions which are called principal directions of the cross section. Now, it is easy to work with the formula, flexure formula that we have derived to find out the bending stresses acting on a cross section. So, just I would like to show you here a particular example. Let us say that we have a beam which is of this type. So, let us say that this is the beam wherein our x axis is located like this, y is located here, and this is our z axis. Now, for this cross section we can find out the direction alpha 1 or the, let us say, angle alpha here, which gives us the direction u, and the corresponding orthogonal direction is v. So, these are the principal directions of the cross section, and note that this is one plane, this is the xu plane. On this plane, if bending moment is acting, then we can use the flexure formula straight away. I repeat that if you have the loading, let us say, acting on the xz plane, then in that case you find that this xz plane is not really a plane of symmetry. On the other hand, if the loading is acting on the ux plane, it now becomes a plane of symmetry because IUV equal to 0. So, now in general what you will have is that you are going to have a bending acting on the cross section. Let us say this is the y direction, and this is my z direction, and this is the CG of the cross section. Now, you will most often be given a bending moment, let us say, about the z axis. So, this is the bending moment. Let us consider its direction to be like this as positive. So, this is mz. Now, this mz, we have the directions u, which is this direction, and the direction v is this one. Now, this moment vector can be resolved into two components without any difficulty into a moment vector along this direction. So, therefore, that will be nothing but mz into cos alpha. So, that gives you the value of mu. Similarly, if I resolve the mz component in this direction, which is minus v direction, we will probably get a component like this. This is the component in this direction of v axis, and therefore, now from this mz we are in a position to get mu as mz cos alpha, and mv let us consider our convention that it will be positive in this direction, that is our positive right hand screw rule. So, therefore, this moment that is acting on the cross section is negative. So, therefore, in this case you can straightway write that mu is equal to mz cosine alpha. So, wherein I am saying that this angle of inclination is alpha, wherein I think will let us show that this angle here is nothing but alpha. So, therefore, mu is nothing but mz cosine alpha. Similarly, mv is equal to minus mz sin alpha. So, I am trying to say that it obeys right hand screw rule. So, if you rotate a right hand screw, it will go in that direction. So, therefore, that is my positive direction. And similarly, in this case I also have the right hand screw rule. If the screw moves in this direction, that is the positive bending moment. So, therefore, that is the rule I have adopted, and the component of this will be really like this, it is exactly opposite. So, therefore, a negative sign comes here. Now, if you consider these two moments mu and mv, they are acting on the planes of symmetry of the cross section, and therefore, without any difficulty you can apply the flexure formula that you have already derived, that is minus sigma x by y equal to m by I equal to E by R. That formula can be directly adopted to calculate the stresses on the cross section. So, we would like to first of all look into a case how to find out the principal cross sections, principal axis of the sections, a given section, and then how do you go about calculating the stresses in a particular case. So, let us look into some examples now, so as to elaborate the calculations that we had just now got. Now, I think we can even straightway write, let me continue on this point, on this cross sections once more. See that here, if I now get back to this cross section again, I have mu acting. So, mu is going to give me stresses which is going to be given by mu, and this mu divided by Iu multiplied by distance of a point in terms of v, that gives us the stresses. Please see this, that your mu is trying to, that is the mu moment, and therefore, my formula would be sigma by v is equal to minus sigma by I beg your pardon, minus sigma by v is equal to mu by Iu. So, therefore, if I use that formula, it will be mu by Iu into v, that gives me stress, and note that this particular moment is going to cause compressive stress in the segment where v is positive. So, therefore, this is compressive stress. So, therefore, my sigma x is going to be minus mu by Iu into v, and similarly mv, look at this mv by IV into distance of a point from the v axis, that is in terms of y, that will give us the stress. So, my stress would be nothing but mv by IV into u, that is the stress. Now, note that for this sort of bending moment, you are going to get positive stress, tensile stress for u positive, and it is going to give rise to compressive stresses on the bottom half of the section. So, therefore, we have tensile stress due to MB and compressive stress due to MU. So, finally, my stresses on the cross section is going to be given by this formula, minus mu by Iu into V minus mv into u by IV. So, that is the total stress at any point on the cross section. So, to calculate the stresses on a section of this type, what are the steps? First of all, you should be in a position to calculate the two principal directions of the cross section u and v, for which IUV is 0. Then from the given bending moment on the cross section, you try to find out what are the magnitudes of the bending moment acting on the axis u and v, and then try to make use of the flexure formula to get at the total stresses. So, we will now try to illustrate this sort of derivation by considering some examples. First, we will try to see the example wherein we are interested in finding out the principal axis of the cross section, then we will apply it to calculate stresses. So, let us consider an example here. So, the section is like this, it is Z inverted Z section, and dimensions are as shown here, very thin section, or rather the wall of the section is very thin, the flange is very thin, so also the wave is also thin, and everywhere the thickness is equal to T, and this dimension semi height of the wave is A. This is the CG of the cross section here, CG of the cross section, and what is needed is that determine IY, IZ and IYZ and also alpha 1, that is the direction corresponding to the principal directions. Now, you should be able to have some guess about the principal directions. Let us look into the figure again. You see here, this is a cross section, we have to find out the two directions for which product moment of inertia should be 0. Now, obviously, we must have the orientation such that some of the portion of the section should lie in the positive segment and some of the portion should lie in the negative segment, then only it is going to work out. So, therefore, most likely I will have a orientation of one of the axis to be like this and the other one will be just orthogonal. So, we will try to see that. So, I expect in this case that my one principal direction will be oriented like this, so that some of the portion of the material will be in the positive segment and some will be in the negative segment and other axis will be like this. Now, let us try to calculate first of all the moments IY, IZ and IYZ. So, if I consider IYZ, to calculate IYZ, I can consider it to be consisted of 3 segments. One is of dimension, let us say A. Yes, please note that this flange is also having a dimension A and this flange is also having a dimension A. So, therefore, I can consider approximately that this portion is nothing but of dimension rectangular segment of dimension A and T, and it is at a distance of A from the Z axis. So, I can use the parallel axis theorem, and now the orientation or the position of this arm and this arm is same with respect to the Z axis. So, I can write the moment of inertia of this segment about Z axis as A T cube by 12, that is the moment of inertia about its own axis, that means actually axis passing through the CG of this segment. Now, I apply parallel axis theorem, that is A into T in the distance of this from the Z axis is A square. So, therefore, I will have A T into A square. So, this is the moment of inertia of this portion about the Z axis. So, now same expression will be obtained for this. So, I can write that for the 2 segments it is going to be 2 times this one, and now this portion which is of dimension 2A and of thickness is equal to T. So, I will have T 2A cube by 12. Now, this particular problem has been given with the condition that that this A, dimension A is very large compared to T. So, therefore, we can ignore this T cube compared to A cube. So, therefore, I can now write this portion can be neglected, and therefore, I will have 2 A cube T for this part, and this is going to give us 2 by 3 A cube T, and these added up together it gives us 8 by 3 A cube T. So, that is neglecting T cube terms. Similarly, if I now go in for calculating the moment of inertia about the y axis, first of all I will have this wave is going to give us 2a t cube by 12 and two flanges about their own centroidal y axis is t a cube by 12 plus area is a t and the C g is at a distance of a by 2 from the y axis. So, therefore, this gives us the value together, and these two when we simplify, we can again, here is a t cube term involved. So, therefore, we can neglect this and we will have then a cube t by 6 plus a cube t by 2, and therefore, we will have 2 by 3 a cube t. So, this is I think quite straightforward. Now, let us try to look into the product moment of inertia. That is something probably you may not be very familiar with. So, let us consider now I y z. Now, as usual we will go for considering the three segments. So, the product moment of inertia for this section can be gotten by considering again this segment, and we can take the area of this segment and multiply by the C g coordinates of this segment with respect to the origin. Similarly, for this segment I can write the area multiplied by the C g coordinates with respect to the origin of the whole cross origin here, or the C g of the whole cross section, and so is the case for this segment also. We can consider the area multiplied by the coordinate of the C g of this segment. Now, obviously, this portion is having C g which is coincident with the origin, therefore, that does not contribute anything. So, we are going to get only contribution from this wave and this wave. So, I will now write, if I consider now this one, then my area is a t and x coordinate of the C g is minus a by 2. So, therefore, it is minus a by 2, and the distance from the z axis is a. So, therefore, it is into a. So, that is the x of x C g y C g. Similarly, for the other portion of the wave we will have for the other portion of the flange. So, it is a t, and herein now the distance again is actually a by 2. So, therefore, it is a by 2, it is now plus a by 2, and this distance is now negative. So, therefore, it is minus a. Therefore, when you add up this, both are negative, and we get now a cube t by 2 twice, and therefore, it is a cube t. So, the product moment of inertia is minus a cube t. Now, we are interested in finding out the section or set of axes which will make the product moment of inertia 0. That means, we are interested in calculating alpha one direction. So, if we just invoke the formula tan to alpha 1 is equal to minus twice I y z by I z minus I y is equal to 2 a cube t 8 by 3. So, this minus becomes plus 8 by 3 a cube t minus 2 by 3 a cube t, which is equal to 1, and therefore, alpha 1 is equal to 22.5 degrees. Now, let us try to see how good was our guess. We now get the direction u1 to be like this, which is oriented at an angle of about 22.5 degree. Therefore, this is my direction u, and obviously the other direction v is like this. So, this is the other direction v, and you see, as we were expecting, that one of the principal direction is to be oriented like this, so that a portion of the material lie in the negative half and a portion lie in the positive half, and we have got exactly as we expected. So, let us now continue further on this. So, we have got now the direction u and v, which are principal directions for the section. It will be nice to calculate the value of IU and IV. So, it is a question of simply applying the formula and getting the values. So, let us do that. So, we have IU IZ plus IY by 2 cosine 2 alpha 1 minus IYZ sine 2 alpha 1. So, that is the formula we derived. So, it is a question of just substituting for 2 alpha 1 as 45 degree. So, once you do that, you finally get the values. I think I will not go through the intermediate steps, I will give you directly the value here. So, finally, what we get here is 5 by 3 a cube t plus a cube t 1 by root 2 plus a cube t 1 by root 2, and this is equal to 5 by 3 plus root 2 a cube t. So, that is the moment of inertia IU, and this gives you value equal to 2.357 a cube t for IU. Similarly, IV I need not go through the similar formula. I can make use of the fact that IV is equal to IZ plus IY minus IU, and therefore, we have 10 by 3 a cube t minus 2.357 a cube t, which gives us 0.976 a cube t. So, that is the value of IV. So, we get both the principal moments of inertia. So, these are the steps to calculate the direction of principal axis of the cross section and the moments of inertia. Let us now try to go for calculation of stresses. So, we will consider now example on calculation of stresses. The problem is shown here. We have a cantilever beam which is fixed at this end, where the cross section is like inverted L. You have the wave of height 5 centimeter and the flange is of length 3 centimeter, and the thickness of the wall is 0.5 centimeter. These are the axes Z and Y, and P is the force acting on this cross section, which is 1 kilonewton. So, I have shown the cross section again here, and already calculation has been done about the CG location, which you could do very easily. It is going to be located at a distance of 0.75 centimeter from this edge, and it is going to be located at a depth of 1.75 centimeter from the top fiber. So, this is the CG location. Now, we have to calculate as usual the directions, let us say we will try to consider that this is my u direction, and similarly this is my v direction. So, we will calculate the directions or find out the directions u and v. We make use of the formula once again, that the value of the moments of inertia are given here. Ij equal to 9.44 centimeter raised to the power 4, Iy equal to 2.58 centimeter raised to the power 4, and product moment of inertia is 2.813 centimeter raised to the power 4. I must tell you that the product moment of inertia can be positive and negative, but never ever these moments of inertia will be negative. So, that is a very typical of this product moment of inertia, that it need not be always positive. So, now the direction of this axis u, which is alpha 1, I won't write it. So, this is the angle I am referring to, alpha 1. So, tan to alpha 1 is equal to minus twice Iyz by Iz minus Iy, and this gives you minus 2 times 2.813 divided by 9.44 minus 2.58, and this gives us a value of minus 0.82, which means that 2 alpha 1 is equal to 140.64 degrees, and therefore, alpha 1 is equal to 70.32 degrees. So, therefore, this angle is 70.32 degree, and you can calculate this Iu and Iv. So, we will straightway write Iu, which is given by Iz plus Iy by 2 plus Iz minus Iy by 2 cosine 2 alpha 1 minus Izy sine 2 alpha 1. So, therefore, if we substitute the value, I will skip the steps. So, this gives us Iu equal to finally 1.574 centimeter raised to the power 4. So, that is the value of Iu, and we can calculate Iv from the invariance condition. So, Iv is equal to Iz plus Iy minus Iu, and therefore, this is 9.44 plus 2.518 minus 1.574, and this gives us 10.384 centimeter raised to the power 4. So, these are the principal moments of inertia. Now, the problem, what is the problem? The problem is that for this particular case, so look at this geometry. For this particular case, I am trying to apply a force here like this, and we are interested in calculating the maximum stresses, bending stresses in the cross section. Think for a while that you have this is trying to, this particular force is trying to bend the cross section about the z axis. So, it is trying to do like this, it will go bending like this, and there will be stresses acting there. Obviously, we expect tensile stresses to be occurring in this region and compressive stresses at the top fiber region. Now, we have to find out the extreme stresses. So, we have now located the principal direction. So, one of the principal direction is this one, which is at an angle of 70.32 degree in the with the z direction. So, therefore, this is your u, this is v. Now, what we need to do, that this force P is going to give a moment of magnitude 0.5 into P, say kilonewton meter, about a z axis located somewhere here, and that moment must be resolved in the two directions u and v as mu and mv. Then we can apply the flexure formula to calculate the stresses, and that is what we are going to do. So, here mz is p into length of the member, and it is positive moment because you see this is going to give a anticlockwise moment, and therefore, it will be positive. So, 1 into 0.5 and hence it is 0.5 kilonewton meter is the bending moment. Now, this bending moment I have tried to resolve it here. Look at this, we have this, that is the mz, this is direction z, and now we have the direction here, this is the u direction, and this angle is equal to alpha 1 direction, and similarly we have the other direction which is v direction. So, now this angle is 90, this moment mz I can write that mu is going to be mz into cosine alpha, and similarly mv is going to be nothing but minus mz sin alpha 1. So, I repeat, mu is going to be nothing but mz. So, the component this one is going to be simply mz cosine alpha 1, and the component which is going to be in this direction, it will be mz sin alpha 1, it will be in this direction, but my positive direction is this, and if we consider our moment to be positive this way, then it will become a negative moment. So, I now have mu is equal to mz cosine alpha 1, and therefore, this is 0.5 cosine 70.32 degrees, and this is nothing but 0.168 kilonewton meter. Similarly, mv is going to be, my positive v direction is this, but this moment is going to be pointed this way. So, therefore, it must be negative, and therefore, it is mz sin alpha 1, and this gives us minus 0.47 kilonewton meter. So, these are the moments. Now, we have to locate for this cross section. First of all, it is good idea to locate the neutral axis. There will be a line passing through the CG of the cross section on which there will be no stress. So, now if I write the expression for stress sigma x, which we have derived little while ago, this is nothing but mu by Iu into V minus mv by Iv into u. So, that is the general form. And now, for neutral axis, what we should have, that sigma x should be equal to 0. So, therefore, for neutral axis, we must have, we substitute the value 168, and I consider it to be Newton centimeter, kilonewton centimeter, that is why I multiply by 100, and this is 1.574 V minus, and this value is minus 47 into 100 into u divided by 10.384 equal to 0. So, that is the line which is going to have no stress acting at any point on it, and this line is going to be oriented therefore with the positive u direction given by beta. So, we can now write from this itself. So, we can write now V by u, which is, let us say, tan beta. So, tan beta is V by u, and this gives us value 470 multiplied by 100 divided by 10.384 384 multiplied by 1.574 divided by 0.168 multiplied by 100, and this is nothing but minus 0.424, and this is minus tan 22.98 degree. So, beta is nothing but minus 22.98 degree. This is something very important. So, let us consider the cross section again. We have got like this. This is the cross section. We have u v directions like this. Now, the neutral axis is going to make an angle of minus. So, this is my direction u, this is v, and it is going to make an angle of minus 22 point, this magnitude we got as 22.98 degrees. So, therefore, this is the angle. So, this is the angle 22.98 degree. So, this is the neutral axis of the cross section. So, this is very important that on this line you find for this cross section. So, if I now look at this cross section, I have a line here which is oriented like this. Let us say that this is the line. For this line, if you consider any point on this line, there is no stress, and hence what you find now, because of the loading, you are going to get compressive stresses on the upper half of the plane, and on the bottom half you are going to get tensile stresses. So, you are going to get tensile stresses to be generating somewhere here, compressive stresses to be generating somewhere there. So, therefore, you can now calculate the stress at the furthest point from the neutral axis. This is the furthest point, because my neutral fiber is going to be located like this. This is the neutral axis. So, you can find out this is the furthest point. Similarly, this is the furthest point. You can calculate the stresses on that at those points. So, quickly I will try to give you the stress at the point A. So, for that you need to calculate u of A, which is nothing but z cosine alpha 1 plus y sine alpha 1, and this one if you calculate after substitution of the values, it is 1.395 centimeter. Maybe I will just write these coordinates so that you get the idea. This is 0.75 cosine 70.32 plus 1.75 sine 70.32. Now, I think let us quickly see this, what I am trying to say. I am trying to now find out the coordinate of this point. It is at a distance of minus 0.75. So, I have written minus 0.75, and it is at a distance of 1.75 from the z axis. So, 1.75. So, that is what I have written. So, this is UA. Similarly, if you consider VA, it is nothing but minus z sine alpha 1 plus y cosine alpha 1. So, once you substitute the value, it comes out to be 1.295 centimeter. So, these are the coordinates. Now, if I am interested in calculating the stress at A, it is going to be mu by Iu into Va plus mv by IV UA, and we substitute the value now. It is going to be 16.8 kilonewton centimeter divided by 1.574 into 1.295, that is Va, plus minus 47 kilonewton centimeter divided by 10.384 multiplied by 1.395, which is UA. So, once we do that, it gives us a stress of magnitude 20.13 kilonewton per centimeter square. So, this is the stress which is compressive as we expected. The stress at this point of the cross section is expected to be compressive, because this is the neutral axis, we expect compressive stresses to be there. Similarly, you can calculate the stress at the point here, which is let us say Q, and we have calculated this stress at Q, it comes out to be 23.0 kilonewton per centimeter square. I think it will be good idea for you to calculate yourself the stress at the point Q and see that this is going to be equal to 20.3 kilonewton per centimeter square.